Namaskar students. In this video, we will take some problems on recurrence relation. So let us consider the first problem. In the first problem, we have to solve the recurrence relation. This recurrence relation is involving the sequence AR. And if we see the order of this recurrence relation, then the order of this recurrence relation is 2 because the highest subscript which is present here in this recurrence relation is r plus 2 and the lowest one is r, and if we consider the difference then we are getting it as 2. It means for writing any rth term we need preceding two terms of the sequence here, the sequence AR. For finding here the solution, for solving here this recurrence relation, we need to find out its homogeneous solution as well as the particular solution. If I talk about the nature of this recurrence relation, it is linear recurrence relation with constant coefficients and it is a non-homogeneous in nature. So this given recurrence relation, this given recurrence relation is non-homogeneous, linear recurrence relation with constant coefficients. We can see here that the coefficients are 1. Then again here the coefficient of this r plus 1th term of the sequence is again 1 and the coefficient of this AR is again 1. So these coefficients, these are the constant. So it is non-homogeneous linear recurrence relation. So here the total solution will be the sum of homogeneous solution and particular solution. So firstly, we will be finding the homogeneous solution. And for finding the homogeneous solution, we will be considering here the characteristic equation. And here, since the order of recurrence relation is 2, so the characteristic equation will be of degree 2. It will be quadratic in nature. So for finding homogeneous solution, we have, let us take here the characteristic equation. And if we write here the characteristic equation, and the characteristic equation is here alpha square, it is quadratic equation in alpha square plus alpha plus 1 equal to 0. So this quadratic equation has two roots. So let us solve this equation and find out its root. So here, if we find out the roots, then alpha will be, this will be minus b, it will be minus 1 plus minus under root b square, which is 1 minus 4 ac, which is minus 4 and is divided by 2a. And here a is 1, so it is 2. So it will be minus 1 plus minus iota under root 3 by 2. Here the roots which we are getting, they are complex in nature. So for these complex roots, if I write down the homogeneous solution, here roots are complex. Therefore, homogeneous solution is given by, here the sequence is A, the subscript which we are using, which is given in our problem is R, and this is H for the homogeneous solution. Let us take two constants because we have two roots here. Let these constants be C1 for the first root, which is -1 plus iota root 3 by 2, this whole raised to power r, and then another constant, let it be C2 -1 minus iota root 3 by 2, this whole raised to power r. So this is the homogeneous solution where the C1 and C2 are constant. Now let us move ahead for finding the particular solution. Now for finding the particular solution, let us see what is here the right hand side. And if we see here the right hand side, the right hand side is here r 2 raised to power r. So the form of the right hand side is, it is CR and we have some polynomial. This is the form here. And if we compare it with this form, then here C is 2 and this polynomial is R. Here the polynomial is of degree 1. Now here this C is 2, and if we check for the roots of characteristic equation, then this 2 is not the root of characteristic equation. So here the C, which is 2, it is not the root of characteristic equation. So what will be the general form here for the particular solution? So for finding the particular solution, we will be taking the general form of the solution, and that general form will be, we will be having this C raised to power r, and then we will be having some arbitrary polynomial of degree 1, because here this polynomial r is of degree 1. So what will be the general form which we will be assuming here? That will be C raised to power r, which is 2 raised to power r here, and some arbitrary polynomial of degree 1, that would be a plus br. And this arbitrary polynomial is involving here two constants a and b, which we will be determining. And once they are determined, then we will be with our particular solution. So let us assume here this general form for solution. To find particular solution, to find particular solution, let us take general form of solution as a plus b r. This is the polynomial of degree 1, and then we have c raised to power r, which is 2 raised to power r. Here in this general form, we will not be having any power of r in multiplication in the product, because here this c, which is 2, this is not the root of characteristic equation. Now we need to find out these two constants a and b. So for finding these two constants a and b, we will be substituting this solution, this general form of solution, in our given recurrence relation. If I name the given recurrence relation as 1, let us name this equation, the given recurrence relation, as 1. Now let us substitute this solution in the recurrence relation. Substituting the solution in the given recurrence relation, which is our equation 1, we have the recurrence relation is here a r plus 2th term of the sequence, a r plus 2. So, and then we have ar plus 1, and then we have ar, and on the right hand side we have r 2 raised to power r. let us substitute in this equation 1. So what we will get, we will be having here, now at the place of r, we will be having r plus 2, because this is the r plus 2th term of the sequence. And similarly, this 2 raised to power r will become r plus 2. Then for r plus 1th term, we will be having this r will become r plus 1. So this will be a plus b r plus 1. And this will be 2 raised to power r plus 1. And in the last term on the left hand side in our recurrence relation is rth term of the sequence AR, and this AR is simply this a plus BR 2 raised to power R. And the right hand side, which is given here in our recurrence relation, the equation number 1, it is R 2 raised to power R. Now, we will be simplifying the left hand side, and then we will be comparing the coefficients, and we will be trying to find here the values of these A and B. So let us simplify it. We have 2 raised to power r plus 2. We can take it as 4, and then we'll be left with 2 raised to power r. And if we simplify this, we have a plus 2b, and we have rb, and then we have 2 raised to power r. Similarly here, this 2 raised to power r plus 1, it can be written as 2. Then we have a plus b plus rb, and then we have 2 raised to power r. And here we have a plus br 2 raised to power r, and this is equal to, on the right hand side, we have r 2 raised to power r. Let us simplify it further. Let us collect the terms of 2 raised to power r, and let us collect the terms which have r 2 raised to power r. So it is 4a, then we have this 8b, then this term has r, so we'll be considering it separately. Then we have here 2a, then we have 2b, then we have, from here we have a, and this is 2 raised to power r. Now let us collect the terms which have r 2 raised to power r. So this is 4b, this one 4b, and here we have 2r, and here we will be taking this r outside, so here it is 2b. Here again we have br, so it will be b, and in all these terms we have r 2 raised to power r, so we have taken it here, and this one. So if we simplify it further, we have here 7a, and we have 10b 2 raised to power r, and this is 7b r 2 raised to power r equal to this r 2 raised to power r. Now comparing both sides, comparing coefficients on both sides, we have this 7a plus 10b, because on the right hand side we don't have this 2 raised to power r, we have this term r 2 raised to power r only on the right hand side. So this 7a plus 10b, this will be equal to 0, and another equation which we will get is that this 7b, this is the coefficient of r 2 raised to power r. So on the right hand side, this coefficient is 1. We can name these equations as equation 2 and equation 3 because we have used earlier equation 1 for the given recurrence relation. From equation 3, we will get b. From equation 3, b is equal to 1 by 7. And using b as 1 by 7 in equation 2, we have 7a, and let us put the value of b, which is 1 by 7. So it will become 10 by 7 equal to 0. And this will give us a as minus 10 by 49. So we have a and b with us. So this implies the particular solution is, you have the sequence A, the subscript is R. Now this is P for the particular solution. And what was the form? The form which we have taken, that form was A plus B R, the polynomial of degree 1, and then C raised to power R, which was 2 raised to power R. Now if we put here this A as minus 10 upon 49, so it is minus 10 upon 49 plus B, B is here 1 by 7 R, 2 raised to power R. So we have evaluated both the homogeneous solution and the particular solution. So the solution of this frequency relation is given by the sum of these two. Hence, the solution of given recurrence relation is AR is the sum of homogeneous solution and this particular solution. So what we get here, the homogeneous solution is, we have two constants in the homogeneous solution, C1 minus 1 plus iota root 3 by 2 raised to power R plus C2 minus 1 minus iota root 3 by 2 raised to power R. And then we have the particular solution, which is minus 10 upon 49 plus 1 upon 7 R 2 raised to power R. So this is the solution of the given recurrence relation, the first given recurrence relation. Now let us come to the second one. In the second one, we have this recurrence relation. This recurrence relation, this is for a sequence by k. The subscript which they are using here is k. And if we check the order of this recurrence relation, then for finding the k plus 1th term of the sequence, we need only one preceding term, which is the kth term. So here the order of this recurrence relation is 1. And also we can see here that if we take the difference of highest and the minimum subscript which are involved here in this reconciliation, then the difference is coming as 1. So that also shows that the order of this reconciliation is 1. And this is again linear reconciliation, and the coefficients are again here constant. Here the coefficient is 1 and here the coefficient is minus 1. And this is non-homogeneous, and the right hand side is here 5 raised to power k. So if we see here this right hand side has the form like c raised to power k. So it depends that whether this c, which is here 5, this is the root of characteristic equation or not, because depending on that we will be assuming the general form of our particular solution. And they are also giving here the initial condition. This recurrence relation is satisfying the initial condition, and one initial condition is given here because the order is 1. And what is that initial condition? That the first term of the sequence y0, this is equal to 3. So with the help of this initial condition, what we will be doing, we will be finding the constants which will be present in our solution. So let us take this problem. It is yk plus 1 minus yk equal to 5 raised to power k, and the initial condition is here that y0 is 3. So let us come and let us try the second problem. We have here the recurrence relation yk plus 1 minus 5 by k. It is equal to 5 raised to power k, and here it is given the initial condition is that y0 is equal to, y0 is given as, if we check here what is y0, y0 is given as 3. So here the y0 is 3. So again here, first of all, we will be mentioning that this recurrence relation is a non-homogeneous linear recurrence relation with constant coefficients, and its order is here 1. So firstly, we will be finding the homogeneous solution, and for the homogeneous solution, we will be considering here the characteristic equation. So if I write down the characteristic equation, here, since the order is 1, so the characteristic equation will be of degree 1. It will be linear equation. And since we are taking the characteristic equation in alpha, so from the first term, we will be getting here alpha, then we have minus, then we have 5. And this alpha minus 5 equal to 0 is here the characteristic equation. And when we will be finding its root, we'll be getting here the one root, which is 5, and this root is real. Now for this real root, this real one root, if I write down the homogeneous solution, so the sequence is here y, the subscript is here k, and this h is for the homogeneous solution. We'll be taking one constant here, only one constant, because we have only one root here. So let that constant be c1, and that root is here 5. So we have 5 raised to power, subscript which we are having here is k, so it will be 5 raised to power k. This is a homogeneous solution. This is our homogeneous solution. We will be writing it in the proper way as we have discussed in the first problem. Now, let us assume here, for finding the particular solution, let us assume here the general form of our particular solution. General form of solution. As we have discussed that the right hand side is of form c raised to power k, and here the c is 5, and if we see here, this 5 is the root of our characteristic equation. Earlier in problem 1, the c was not the root of characteristic equation, but here the c is root of characteristic equation, and if we check the multiplicity, then the multiplicity of this root 5 is 1. So the general form of the solution, it will be having r in it, because here the multiplicity is 1. So the general form of the solution will be some constant a, and sorry, it will not be r, since here the subscript which has been used here in this problem is k. So we will be having k here, k, and this k will be coming with power 1, because the multiplicity of this root alpha, this 5, is 1. If suppose we have this 5 with multiplicity 2, it is repeating 2 times, then we will be having in the general form of our solution k square. But since here the multiplicity is 1 only, so we will be having k, and ak, then we will be having c raised to power k, which is here 5 raised to power k. So this is the general form of solution, and once we have assumed the general form of our solution, we will be putting this general form in the given recurrence relation. So if we put it in the given recurrence relation, I am putting here it in the given recurrence relation. It will be, the given recurrence relation is this one, this equation 1. So it will be a, this is k plus 1th term. So this a is constant, which we need to determine, and this k will become k plus 1, and similarly it will become 5 raised to power k plus 1, because here we are finding the k plus 1th term. Then we have the next term in our recurrence relation as minus 5, and the kth term of the sequence. So the kth term of the sequence, it will be a k 5 raised to power k, and the right hand side is 5 raised to power k. What we have done here, this general form which we have assumed, we have substituted this in the given recurrence relation. So I have not written here what we have done, substituting the solution, the solution which we have assumed here, substituting this solution in given recurrence relation, which is equation 1, we have this one. Now, by comparing the coefficients on both sides, we will be trying to find here this constant A. So here we have 5 raised to power k plus 1. We can take here 5a, and it is k plus 1, and then we have 5 raised to power k, and then we have 5ak, 5 raised to power k, and on the right hand side we have 5 raised to power k. Let us collect the terms. We have 5ak, then we have 5a, then we have minus 5ak, and this 5 is to power k is present in all these three terms. So it is like this. Now let us compare the coefficient of 5 is to power k on the both side. This will cancel out. So we will be having only 5a on the left hand side. So comparing coefficients, we get 5a, and here on the right hand side this coefficient is 1. So we get 5a equal to 1, and this will give us that a is 1 upon 5. Now the solution, thus particular solution is the sequence y, the subscript is k, p for the particular solution. The particular solution was a, k, 5 raised to power k. So let us put here this a, which is 1 upon 5, 1 upon 5, k, 5 raised to power k. So it will be k, 5 raised to power k minus 1. Now let us write down the solution. The solution is given by the sum of the subscript is k, and the sequence, the notation here for the sequence is y, yk. So the solution is yk equal to the k term of the sequence is given by the sum of homogeneous solution. The homogeneous solution is here C1, 5 raised to power k, and we have only one constant in the homogeneous solution because it is recurrence relation of order 1, and the particular solution is k, 5 raised to power k minus 1. Now, using the initial condition, because when the initial condition is given, using that initial condition, we will be finding this constant C1, which is present in the homogeneous solution, given that the first term of the sequence, when k is 0, this first term is 3. This implies, if I consider here k as 0, by 0, it is equal to 3, and this will become C1, 5 raised to power 0, which will be 1, and then we have k here as 0, so this second term will vanish. So this will give us directly C1, and C1 is here 3. So if we put here the value of this constant C1, this implies this yk, the kth term of the sequence, this is 3, 5 raised to power k plus k, 5 raised to power k minus 1. So this is the solution of given recurrence relation of order 1. So in this way, we can solve the recurrence relation. Firstly, we will be assuming the characteristic equation. Depending on the nature of roots of characteristic equation, we will be writing its homogeneous solution. And then on the basis of this right-hand side, we will be assuming the general form. For finding the particular solution, we will be assuming the general form of our solution. That general form will be involving some constant. So we will be putting that solution in the recurrence relation, and by comparing coefficients, we will try to find out those unknown constant. And once we are able to find out the constant, we have the particular solution with us, and the sum of homogeneous solution and the particular solution, it will give the solution of given recurrence relation. So in this way, we can do the other problems based on this concept of recurrence relation. Thank you. Have a nice day.